Hi, this is joint work with Seth Bullock, but I think if he was giving the talk, it might be quite different. So I'm the one to blame for all my infelicities. This is a poem in Gaeilge on Céad Fléach. Last two lines are Dinodger on VA, Gerlua Tall na Tyrnave. Gaeilge is the historic language of Ireland. These days, it's spoken by maybe, well, everybody speaks it a tiny bit. Maybe 20,000 people speak it as a first language. It's quite different from English, as you can see. In particular, it has these initial mutations. So the word Fléach, the H there is grammatical. In other contexts, the word would be Pléach. Gaeilge, divided from the other Indo-European languages, the last common language was maybe 5,000 years ago. So about 20,000 speakers now. But that's a kind of a recent disaster. So this is a map of how many people spoke Gaeilge in 1800. The black areas are places where almost everybody spoke Irish, where more than 90% of the population was Irish speaking. And you might think, well, those areas in black, if you know Ireland at all, I'm from here, you might think that not many people live there anymore. But in fact, in the early part of the 19th century, the period represented by this map, those areas were very densely populated. They were among the most dense populated parts of Europe. More densely populated, although they were rural areas, more densely populated than many cities are now. So what happened? Well, this is kind of what happened in 1800. That marks the Act of Union. Ireland became part of the United Kingdom. And it's suffice to say, it didn't really go very well. In 1840, there was a famine. The people, well, you can see the population drops off quite dramatically. Maybe 1 million of those people starved to death, and the rest of them moved. And where they moved to was largely English-speaking countries. So you had an efflux of the Irish population to English-speaking countries, and indeed in Ireland the use of Irish more or less completely collapsed. So although in 1840, when the population peaked at 9 million, 5 or 6 of those 9 million spoke Irish. By the time you get to Irish independence in 1920, the population was down to whatever it is, 4 or 5 million, and continued to fall for the next 50 years, unfortunately. But those people largely were English speakers. And so you have this disaster, I suppose, where Irish stopped being the main language of Ireland, and where an awful lot of Irish speakers went to English-speaking countries, England and North America. And so you would expect that the English language, which is famously a mix of different languages and willing to take on vocabulary from the languages of the world, you'd expect English to be full of Irish words. So this is a list of basically all the words, Irish words, and some of them are actually Scots Gaelic as well. It's hard to tell the difference. But this is a list of all the Irish and Scots Gaelic words in English. And as you can see, it's not that many. And many of those words are probably words that you don't know as well as I do as a speaker of English Irish. So some of them are I mean, weirdly, 3 of them are related to glacial geography, the Curry, the Esker, the Drumlin. Lots of them are kind of words for mythical creatures for some reason. Banshee, Bogeyman, Gombeen, Luthermon, Sleveen. Well, Sleveen isn't a mythical creature. That's just a greedy man. Which is certainly not mythical. But the ones in grey, although they're actually some of the most common words, they're words where the meaning in English is completely removed from the meaning in Irish. So phony is actually from fáinne, which is the Irish for ring, and it relates to the, I hope, false allegation that my country people used to commit fraud with brass rings pretending to be gold rings, phony rings or fáinne. So my point is that although it's considered a sort of truism that languages frequently adopt words or structures from other languages, it's just not that true. And languages are remarkably stable. That's not to say that they're completely stable. I mean, English is clearly a mixture. It's one of the, apart from Maltese, it's one of the most mixed languages you can think of. And as you can see from these 2 examples, it's quite clearly a mix of French and Danish. But that happened because of a cataclysmic event. It happened because of the Norman invasion of England. And so in the churn of the Norman invasion, sure, English became a mixture. But more asymmetric language contact appears to involve very little change to the dominant language. And so I've been interested in this, and I wanted to try and understand it, or to understand if that's a sort of natural consequence of the nature of the dynamics of the evolution of language. Yeah, sorry, this is just finally to finish this off. This is something written in 1726, and as you can see, it's completely readable to the modern eye. You know, languages do acquire new words, obviously. You know, if you think of the Indian or Hindu words in English, they often relate to things that English people hadn't encountered before they went to India. I mean, largely food that had a taste. But you know, but apart from that, languages are remarkably stable. And one version of this might be, you know, it's a population problem or population dynamics. You know, you have one type of people and you have another type of person, and these people aren't going to start wearing suits because they've met Bill Grundy, because there's more of them than there are of him. So, you know, maybe the stability of language in asymmetric language contact is a population phenomena. But I was, and with Seth, I was interested in the possibility that it's actually intrinsic to the evolution of languages themselves. It's a property of the evolution of languages, that the forces or the pressures that make languages what they are also make them stable. And so we wanted to look at simple models of language evolution. And in particular, there is a classic model of language evolution, originally due to Simon Kirby and his co-workers. They invented around 25 years ago now, the so-called iterated learning model. And you know, you might think that coming up with agent-based models of language evolution would be simple. You just get, you know, two agents to talk to each other. But the problem there, you know, play some communication game. And the communication game we're going to play here is going to be very simple. We're going to have some space of meanings. And in fact, the meanings are just going to be binary 8-bit vectors, some space of signals, which are again going to be binary 8-bit vectors. And a language, of course, is a mapping from meanings to signals. And so you'd think it would be easy to set up agents that can talk to each other. There's some reinforcement or something. And then in trying to understand each other, they'd come up with a language. But the problem is actually, the problem is too easy for them. So, you know, they don't produce compositional languages. Our languages aren't always completely compositional. I mean, when we're talking about hair color, for example, we refer to people as having blonde hair. And in doing that, we're referring to a color that in other contexts we might call yellow. Yeah, so, you know, normally speaking, if something's yellow, we call it yellow. In the context of hair, we call it blonde. And if you get agents to talk to each other, if you try to come up with an agent-based model of language learning, that's what they do. They find perfectly good ways of communicating, but they don't do it in a compositional way. When talking about one type of object, they'll use one adjective. In talking about another, they'll have a different meaning for the same adjective, or they'll use a different adjective for the same meaning. They lack compositionality. And so what the iterated learning model does is it is an agent-based model of language evolution that evolves language towards this nice property, which is compositionality. And the key to it is that there is a bottleneck. So here, it's an agent-based model with just but at any given time, there's two agents. There's a tutor and there's a pupil. And the tutor has a language that is a map from meanings to signals, and it teaches this language, or tries to teach the language to the pupil. The pupil then at some point grows up and in turn becomes a tutor. So here's the pupil, and now it's grown up and it's become the tutor. But the key point is that when the tutor is teaching the pupil, it only teaches a subset of the whole language. And that, of course, is in some vague way realistic. When we're teaching our children to speak, we tell them an awful lot about, you know, lorries, cars, and apples, dogs and cats, but we don't produce for them, we don't enact for them the whole of whatever language we're teaching them. We give them a set of exemplars, and then in the rest of their life, they're forced to generalize from those exemplars to produce their own language. And in the agent-based learning model, the pupil is generalizing from the subset of the language that it's being taught by the tutor. It generalizes from that subset when it is itself teaching. So the idea is that these bottleneck subsets are different subsets every time. And so there's a process of learning and a process of generalization. And through the turnabout, through those two processes, the language evolves. And so again, here we are. So there you have a space of signals, you have a space of meanings, you have an encoder, which encodes, oh, it's backwards. I think that's in the paper. Okay, so you have an encoder which encodes meanings to signals, and a decoder which decodes signals to meanings. The decoder is a neural network in the iterated language model, whereas the encoder is a lookup table. So basically, each agent has to have an encoder and a decoder. The encoder encodes, the decoder decodes. The decoder is a neural network. The encoder is a lookup table. This is the original iterated language model, and this just summarizes what I said before. The tutor provides examples, and the pupil trains its decoder. So the pupil learns to decode. The tutor uses its encoder to provide the examples. Then the child grows up. And here there's a subtlety. The child has learned a decoder, but to become or the pupil has learned a decoder. To become a tutor, it needs an encoder. And so in the original iterated language model, there is a step called an obversion. And that's the point where the child decides it's now learned. It takes the decoder it's learned, and it turns it into an encoder. So it takes the neural network that it has trained from the exemplars provided by its tutor, and in some sense it inverts it, although obviously it's not a direct inversion, or it's not in the matrix sense an inversion, but in some sense it inverts that mapping to produce an encoder, which is what it's going to use. It's going to then randomly think of meanings and provide the signal corresponding to those meanings to the pupil. And again, it's in that turn and turn about series of those iterations that that the language develops the nice properties a language should have. And this is just a graph that shows that. So expressibility and compositionality are in the context of this very restricted language, which, as I said, is made of 8 or 10-bit meanings and 8 or 10-bit signals. Expressivity and compositionality measure this nice property of the same bit coding for the same bit, and all possible meanings having a code. And across generations, this iterated learning model produces what you might call a nice language. And once it's produced what you call a nice language, this S for stability, it kind of settles down. And so the iterated language model, due to Kirby et al., is this very neat, very simple agent-based model of how languages might evolve towards having the nice properties that languages should have. Now, there is a problem with this model, which is this obversion. It's as if you spoke to your child, for 4 or 5 years, thinking of meanings, showing them encoding using your language, the word for the meaning. So you think, look at, the dog is running down the path. You then encode that into the dog is running down the path. You say that to the child while pointing at the dog running down the path. The child remains entirely mute for 5 years. It then sort of switches off for a while it inverts this vast matrix of all mappings between everything it's ever going to have to say in its life and every possible meaning it'll encounter. It then it's now able to speak, and the child is then an adult, and the child speaks. The adult teaches a new child. So that stage in the original iterated learning model is very unrealistic. So one of the things that Seth and I did, along with a student, Jack Bunyan, is that we came up with a new iterated language model, which I just want to mention briefly because it's the iterated language model, learning model that we use for this work, but also we think it's quite interesting. In this new iterated language model, both the encoder and the decoder are neural networks. And you think, well, why didn't you do that from the start, or why did Kirby et al. Not do that? And the problem is slightly that the problem there is that if you just do that and naively, and the agent both learns a decoder and an encoder as neural networks, these are simple feed-forward, single hidden layer neural networks. If you do that, then the sort of tension that you have in this sort of generalization process that's supposed to drive you towards compositionality, the tension there is between expanding the meaning. So, if you have the word elephant means very well, An example is the word kangaroo. Originally, the word kangaroo meant a very specific type of kangaroo, but when Europeans came to Australia and asked the people there what the animal was called, they said it was a kangaroo, and they assumed they meant all kangaroos and not just that specific type of kangaroos. There's a movement towards overgeneralization if you just do the naive thing. So to actually make the iterated language model work, in the context of to make the iterated language model work entirely with neural networks, you need also to have an autoencoder stage. The child is taught examples by its adult, but it also tries to imagine how to say things. So it sees stuff around the place, and it tries to imagine how to encode that, and then checks that that corresponds to what it thinks it sees. In other words, the child sees a dog running down the street, it thinks to itself, dog running down the street, and it checks that it understands the words dog running down the street as meaning a dog running down the street. So to get the iterated language model to work with purely neural networks, our insight was that you need to include this autoencoder that you get by chaining together the decoder and the encoder. And we believe that in itself is an interesting point because we believe that in itself is, that works. It produces languages that have these nice properties. But most importantly, we think that that's an interesting thing. It shows that for languages to evolve without this obverter nonsense, you need a sort of internalization of language. And so our hypothesis is that the language starts to evolve when people start to use utterances as a tool for thought. But that's not what we want to talk about, or I want to talk about now. I want to talk about language contact. So in this experiment that I'm going to report on, you have two languages, an A language and a B language. They're both compositional languages. So you take your set of meanings, you find a language that maps it to utterances or to signals in a compositional way. You have two of these languages, A and B. The original tutor, the first tutor, starts off with a mixed language. It's a mixture of A and B, and the proportionality of mixing is given by P. So P equals 0.5 means that the A and B languages are equally contribute to this mixed language that the first tutor teaches to the pupil. And if that happens, this little a and little b, so across the bottom now is generations. We have the language evolving, the language that's been evolved by this iterated language model, learning model. And A and B is the distance of the language from the original A language and the original B language. And what you're seeing in these traces is 50 example evolutions. And as you can see, what happens is if the languages start off half and half, is sometimes they end up looking like A, sometimes they end up looking like B. Most often, they end up looking like neither. You get a completely new language. In this case, one language is slightly more dominant than the other. In that case, you end up with a language that looks mostly like A, usually. Sometimes it looks completely like A. Sometimes it looks like neither. Once or twice, it manages to look like B. But most often, it looks quite like A, but is quite changed. But then if you move even further away, the tendency is always to return to the original A language. In other words, this process of iteration that allows languages to become compositional also stabilizes them so that in language contact, you tend to see the dominant language win out. And this is just the same thing plotted against P. And so very quickly, the dominant language becomes dominant. And as you increase the size of the signal space and the meaning space, in fact, this transition curve becomes more and more sharp. And so that's the conclusion. We wanted to see whether the process that makes languages nice or like languages also stabilizes them in situations of language contact, which is consistent with what appears to actually happen when two languages come together. Thank you.